Hello, my name is Benjamin Giblin and I'm a postdoc at the University of Edinburgh. My talk, titled Weak Lensing Cosmology, Taking the Path Less Travelled, is all about exploring alternative statistics that you can measure from weak gravitational lensing data and demonstrating that these alternative statistics can actually be used to obtain more precise constraints on cosmological parameters compared with the statistic that is used more routinely. So to begin with in this talk, I'm going to introduce the idea of cosmic shear, which is basically the way in which we use weak gravitational lensing to constrain cosmological parameters. I will then introduce some alternative statistics that we can measure from weak lensing data. These are called the weak lensing PDF and clipped shear correlation functions. After that, I will show some results from simulated cosmic shear analyses using these new statistics and contrast them with the results that you get from the more standard analysis. I'll then finish by summarizing these results. So to begin with, cosmic shear. This is the process whereby we constrain cosmological parameters using weak lensing data. Weak lensing data consists of images of tens of millions of distant galaxies, often out to redshifts of approximately 1. So the light from these galaxies has traveled to us to be detected by our telescopes here on Earth. And in the process, the light from all those galaxies has been very weakly gravitationally lensed by the large scale structure that is in between us and those galaxies. And this very small lensing effect causes the observed shapes of those galaxies to be slightly distorted relative to their intrinsic shapes. An exaggerated depiction of this is shown in the white box on the bottom of this slide. You can see that the observed images of these galaxies here shown in the white box differ slightly from the intrinsic shapes of those galaxies as seen in the background. So the distortions that manifest in these galaxy shapes caused by weak lensing is what we call shear. And the amplitude of this shear is sensitive to cosmological parameters, specifically because it is the large scale structure of the universe that's causing this lensing effect. But how do we quantify that? So typically the way this is quantified is using a statistic called the 2-point shear correlation function. So this consists of measuring the ellipticities of the tens of millions of galaxies in the data set and measuring the correlations in those galaxy ellipticities as a function of their angular separation theta. And the shear correlation function is sensitive to cosmological parameters. So you can compare that measurement from the data to a theoretical prediction, which depends on these parameters. And namely, weak lensing is sensitive to the mass energy density of the universe, omega m, and the amplitude of density fluctuations, sigma 8. So here we can see the constraints placed on those two parameters from the most recent weak lensing analysis by the Kilo Degree Survey, or KIDS, and this was published in Asghari et al. 2020. So there is 3 different banana-shaped contours plotted on here, and they're all from the weak lensing data. They're just different ways of quantifying the weak lensing signal. And you can see this banana-shaped degeneracy because weak lensing finds it difficult to tell the difference between a large value of omega m and a small value of sigma 8. This would equate to a universe with a lot of matter that is weakly clustered, And then the inverse of that, which would be a small omega m, large sigma 8, i.e. a universe with not much matter, but it is very strongly clustered. Those two types of universe would cause similar lensing signal. Also pictured on here, you can see the constraints from the analysis of the cosmic microwave background by the Planck mission. That's shown by this very small red circle here. And the very small amount of overlap between the lensing constraints and the constraints from Planck is what is often referred to as the lensing CMB tension. The fact that we're getting slightly discordant results for these parameters from lensing and the cosmic microwave background could be a sign that the standard model of cosmology is incomplete. So what is of great interest to the cosmological community at the moment is to investigate this tension. And the way I am doing that is by trying to shrink the size of the weak lensing constraints, i.e. get more cosmological information out of weak lensing data to more thoroughly and robustly investigate this tension and whether it is real or if it is just a statistical fluctuation. Okay, so let's move on to how we get more information out of weak lensing data. And this consists of going beyond the standard weak lensing shear correlation function. Now, there's many different statistics that you can measure from weak lensing data, but the two that I explore in this work are called the lensing probability density function, or lensing PDF, and the clipped shear correlation function. I'll explain both of these statistics in the coming slides, but first of all, I'll just say that they both rely on a quantity known as the convergence. And the convergence is simply just the projected matter density across the sky that is inferred from weak gravitational lensing. To give you an idea of what that looks like from real data, here is the convergence map, which was measured from the kilo degree survey data over their observations of the recent years. Okay, so let's first take a look at the lensing PDF. So the lensing PDF is simply a histogram of the projected density, that is the convergence. On this figure here, you can see how the lensing PDF varies as a function of the amount of smoothing which is applied to the density map. From the density map, which is shown in the top left hand of this slide, you can see a density map which features a very large amount of smoothing. And this manifests in a very narrow lensing PDF. You can then see how this changes as you calculate the PDF from maps with progressively less smoothing. And this results in PDFs that are progressively broader. So these different PDFs are extracting cosmological information from different physical scales. And we find that by combining these, the lensing PDFs of maps that have been smoothed with different scales, we can extract much more cosmological information than we could if we just used one PDF measured from a map with a single smoothing scale. So now let's take a look at the next alternative statistic, which is the clipped shear correlation function. So clipping is a transformation that can be performed on cosmological density fields. And what clipping does is it specifically targets regions of that density field that are very high density and are on small scales. And it suppresses the signal that comes from those high density regions. This is illustrated by the maps on the left-hand side of this slide. The upper map is what we call the unclipped map. It contains all of the signal, including the high density small stuff. The lower map is what we call the clipped map. It is basically the same map, except that the high density regions, the signal there has been suppressed with this transformation called clipping. So we can essentially derive two different types of shear correlation function from these two different types of map. And these are shown on the right-hand side of this figure. The black line here is showing the standard shear correlation function that's associated with the unclipped field. The orange line, however, is this new statistic, the clipped shear correlation function associated with the clipped field. So we explored clipping and its applications in lensing in a paper published in 2018. And what we found was that the clipped shear correlation function does in fact have independent cosmological information of the standard analysis. So this might sound a bit counterintuitive, the fact that you can get independent information out of some data by suppressing the signal from certain regions in that data. The answer to that riddle relies on the fact that clipping specifically targets high density regions where gravitational collapse has become nonlinear. And we know that the standard shear correlation function is suboptimal for extracting information from fields that contain those regions of nonlinear gravitational collapse. It essentially doesn't model them very well. So the idea here is that the clipped shear correlation function more optimally extracts cosmological information from the clipped field than the standard correlation function does from the unclipped field. And by combining these two statistics in a cosmological analysis, the idea is that you can obtain more precise constraints on cosmological parameters. So now that we have introduced these two new alternative statistics of weak lensing, let's think about how we model their cosmological dependence. So the necessity to model the cosmological dependence of these statistics is illustrated by this equation for the likelihood. This is the thing that you have to evaluate in order to find the best fit cosmology for your data. So this gives the likelihood of some given data, D, given some cosmological parameters denoted pi. So in this equation, you've got the difference between your data and the model of your statistic as a function of pi. So in a standard weak lensing analysis, we have an analytical model for your correlation function and how it varies with cosmological parameters. But with these new statistics, we don't have that. So this is where numerical simulations coupled with machine learning come to the rescue. So the simulations that we're using in this analysis are called the Cosmoslicks suite, and they were published in this paper here in 2019. The Cosmoslicks consist of 26 independent cosmologies, each of which varies as a function of 4 different cosmological parameters. Those parameters are the mass energy density, a parameter called S8, sometimes called the lensing amplitude, and this itself is a combination of 2 parameters, omega m and the amplitude of density fluctuations sigma 8, which we talked about before. Also varying here are the Hubble parameter h and the dark energy equation of state parameter W0. So what's being pictured here is the 26 different cosmologies and Cosmoslicks projected into each of the 2-dimensional parameter spaces in this overall 4-dimensional simulation suite. So essentially, we can measure our new statistics from these simulations, and then we can use a machine learning algorithm to train on those simulations to create a model of how our statistics vary with these cosmological parameters. So specifically, the machine learning algorithm we use is called a Gaussian process emulator. And essentially all it does is just interpolate from the cosmologies measured in the data to arbitrary cosmological parameter configurations that are in between. So it is how we construct a model for our statistic as a function of cosmological parameters. So now we have a model for our statistics as a function of cosmological parameters. One other ingredient that is necessary for this cosmic shear analysis is what is denoted as sigma here. This is the covariance. So this is a measure of how your statistics vary and co-vary with one another. And again, we use simulations to measure that covariance. But once that's done, we have all of the ingredients we need to evaluate the likelihood, and we can perform a cosmic shear analysis. Because we're looking at these statistics for the first time, what is prudent to do is to perform an analysis using a mock data vector, one in which we know the ground truth cosmology. So that's what we do. First of all, let's look at results for the lensing PDF. Here you can see the constraints on the 4 cosmological parameters that vary in the simulations. In orange, you can see the constraints from the PDF, and in blue are the constraints from the standard analysis using the 2-point shear correlation function. Also shown in light blue by the crosshairs is the ground truth cosmology of the mock data vector. So you can see both statistics obtain unbiased results, as you would expect. So you can see by eye that the PDF actually obtains tighter constraints than the standard analysis. And the most significant constraints come for these 2 parameters. So for the S8 parameter and the dark energy equation of state parameter W0, we actually see 30% improvements from the PDF analysis relative to the statistic which is used routinely. Okay, so now let's look at the results for the other statistic, the clipped shear correlation functions. Again, here I'm showing the blue contour, which corresponds to the standard shear correlation functions. Then in pink, you have the contours from the clipped shear correlation functions. And in green, you have the results for the combination of those 2 statistics. So the clipped shear correlation functions themselves, they don't provide more precise constraints than the standard analysis on their own. And that's expected given some of the work we did in the proof of concept analysis published in 2018. But what is crucial is the fact that the combination of the clipped and standard analysis, they do provide tighter cosmological parameter constraints relative to the standard analysis alone. So this confirms that the clipped correlation function does indeed contain information that is independent of the standard analysis. And again, we see significant improvements, but in this case, we find that they are mostly for the omega m parameter, where we see a 30% improvement. And again, for W0, we see a 25% improvement for that parameter. Okay, so to summarize, we've looked at 2 different alternative weak lensing statistics, the lensing PDF and the clipped shear correlation function. And we have found that these 2 statistics, both of which they can offer improvements on cosmological parameters at the level of 25 to 30% compared with the conventional analysis. Finally, I'll just say that the CosmoSlick simulations that we used in this analysis, they're available upon request. Please get in touch. And one thing that I didn't mention is that there is a variant of these simulations that includes weak lensing systematics, including baryonic feedback and intrinsic alignments. So we're going to look at how these systematics affect our statistics in the future.